All right, class, let's begin. We are going to do 3.6, but what we have to do is we're going to take about 10, 15 minutes to fill in some stuff that we needed to do from 3.4. So I mentioned it really, really fast at the end of 3.4, but I really wanted to unpack it. So let's go with it here. So it's the leftover stuff from 3.4. So do you remember that dx of e to the x is e to the x? That's cool. What we want to know is this is a very specific exponential function. And right at the end, when we were doing 3.4, I said, oh, don't forget, this is the rule as well. The derivative, let's see if this was right. Yeah, the derivative of a to the x is equal to, now let me write it just to make sure I wrote it correctly here. It's going to be a to the x ln of a. All right. And I just kind of wrote it on the board, but we really did not discuss it. So I want to just take the time now to discuss that little piece. And then after that, then we'll jump into 3.6. So let's go with it here. So we're going to actually prove it and put it together. Let's go. So from algebra 2, we know a few things here. It's going to be 1, 2, 3, 4, 5. 4 things that we know. All right, so let's go through each of these slides here. So I know it's been a long time. It's been 2 years. But I want to know if you know what is the answer to this guy. All right, and if we want to, we can solve it. So take your guesses. Go for it. Okay, so then let me solve it. Let's see if we'll get what you think it should be. So what I would do is I'm going to start off with this little 5 to the third power. So I'm thinking 5 times 5 times 5. 5 times 5 times 5 is 125. Remember what log powers are asking us. Log powers are asking us what number or what exponent do you put on 5 to give you 125? So what number do you put on 5 to give you 125? That'd be just 3. So this whole process really just gives us an answer of 3. We could have just cut it short and really just took that 3 and just set it as the answer. Right? So the shortcut way, log base 5. If you have a log with the same base, the same value, then the answer just becomes the exponent. You can just cross that out and it gets you a 3. That's cool. Oh, by the way, sorry, you don't have to write these down unless you want to. I will have the rule right at the end in order for you to write it down. Just kind of think with me as we go. So I'm going to just put some random number here. So log base 7 of 7 to the, I don't know, 25, just for the fun of it. Answer is, I don't want to take 25 powers of 7, but I know that the log base 7 and the value of 7 are going to cancel, and the answer would just be 25. So here is the generic. So this one you want to write down. Log base b of b to the x is just equal to x. All right, the other one you want to write down is ln of e to the x. What's that going to give us? Well, ln and e, they should cancel because ln, the ln function, that's just a way of writing log base e. So really that's what happens. And the log base e and e cancel, just like the ln and the e should cancel, and the answer is just x. So that little guy is important as we will go through some of the work here. So if you see an ln followed by e to the x, or by 3, or by 12, or by any value whatsoever, it's just going to be that value. Okay, boom. One thing we need to know from algebra 2. The next thing. Next thing, what happens if I have a base and then I have the log with that same base in the exponent? So let's do one that works out well right there. So think with me if you want to. If you want to write it down and it kind of helps for you to write it down, kind of learn it, that's fine too. But here we go. I'm going to work with the exponent only, just that little piece right here. So log base 5 and 125. What exponent did you put on 5 to give you 125? That's 3. That little piece should just be a 3. Then the question is, what is 5 times 5 times 5? 125. So there it is again. That little 125 becomes the answer. And a shortcut to it, let's do the shortcut with some other numbers here. Log base 7 of like 143, just some random number. All right, what happens, just like over here, I can cut the 5 to the log base 5. I can cut the 7 to the log base 7. And voila, answer is 143. Okay, let's write the general rule. Here's the one you want to write down. So any base called a to the log of base called a of x will just give me x. And if you got this, can you write down the ln equivalent, the natural logarithmic equivalent? All right, here it is. So that log specifically would be e. This would be ln of x. And these two should cancel themselves out and give us x. So again, I will put a box under that one. That's important. All right. Next. And then this one from algebra, just for us to remember. Exponent. So if you have 3 to the second to the 4th power, what happens to the exponents if one is inside the parenthesis, one is outside the parenthesis? We just multiply them together, 3 to the 8th. Cool. So the general rule is x to the m to the n. It would be x to the mn. There it is. Okay, one more rule from algebra before we get started. Let's take a look at this here. So log base 4 of 4 to the 3. Haha, I know you know the answer to this one. I'm going to switch it up on you just a little bit here. What happens is we can do something with this little 3. It's the exponent of your index. This little exponent can move all the way out in front and be the multiplier. You guys remember that rule from algebra? So I could put the 3 in front, and this would just be log base 4 of 4, and technically that 4 now is becoming 4 to the 1. So I think we just learned this one. Log base 4 of 4, that cancels. And you got 3 times 1. Look at that, still the same answer, it's just 3. Right? But the rule is I can make this 3 as a multiplier. That's the problem. That's the good thing there. Let's put some generic numbers here. Let's see. So log base 5 of the value of 6 to the 7th power. I can rewrite this, and it'll be the exact same thing as 7 going in front, log base 5 of 6. That 7 just kind of went right in front of that log there. That's all, and that will give us still the same answer. Okay, the general principle, here it is, log base b of any value a to the r power. Where does the r go? All the way in front as a multiplier to log base b of a. And then you know what also? If it's just multiplying log base b of a, I can also put it at the end. So putting this at the end, I can write it as like this. I do like to have parentheses here because it really tells me I'm multiplying r towards everything. If I just have the r here without the parentheses, it kind of gets confusing because it might think that we're just multiplying a and the r only. That's not the case. R is multiplying the whole log base b of a. All right, converting this to ln, here we go. So ln of a to the r. Where can the r go? R in front. I got ln of a. Or if I wanted to, I can put that r all the way at the end. And in that case, I'm just going to put a little parenthesis here. So there it is. ln of a times r. Okay, I'm going to skip a little something here. All right, and one little trick we got to do. Here's our little trick. if I have a to the x, just some kind of number to the x power, here's the little trick I'm going to do. I'm actually going to put in a base of e, and I'm going to make ln go into the exponent. I think we've seen that before, is that right? Remember, we can cancel this out, right? And if we cancel this out, it gets us back to a over x, right? So therefore, I know that's true right here, right? That's the same thing. If I cancel the e to the ln, I just get a to the x. Those are the same. Okay, that's cool. Okay, another little trick, and then we'll get started. E to the ln of a to the x. If that is sitting there as well, what can I do with the x? Remember, it's the exponent on the a. That's cool. So hold on, I can move the x out in front. It becomes e to the x ln a as a multiplier of ln of a, or I can move it to the back, and all that is all the same, right? X is just multiplying there. Okay, now we are ready. We're ready to get started. It's a cool little proof. So our job is we're trying to figure out how to take the derivative of any generic value to the x coordinate. So remember, if this was e to the x, it just gives us the same thing, right? But if it's like, say, 2 to the x, 3 to the x, 4 to the x, 12 to the x, how would we do that? And so here's our tricks. Let's put it all together. If you've been paying attention, we did great. Here it is, the derivative of that. And I'm going to use my little trick. Tell me if you guys agree that that is still the same thing. Yep. Okay. So the x could be a multiplier. There it is. The x could be a multiplier in front or at the back. So I'm going to put it at the back already. So this is e to the ln of a times x. Okay, cool. Hold on. Don't I already have this is just taking derivative of e now. Is that right? Oh, hold on. This is the derivative of e with the chain rule, right? Because ln of a times x is actually inside e. So the chain rule says the derivative of e to the whatever is just going to be the exact same thing. It's going to be e to the whatever is in the exponent. There it is. I'm going to write this one right here. This is the value I want here. Times, and again, these are the same thing, right? So I want this value. I want the middle value to make a derivative, just because I can choose anyone that I want. Then I'm going to take the derivative of ln of a times x. Von, so this is interesting. Notice x is our variable, is that right? So what would be the derivative of something times x? All right, so let's see if we can make this happen here. So e to the ln of a to the x multiplied by, what's the derivative of ln of a times x? It'd just be ln of a. How come you say? Because ln of a is just a number. It's kind of like, what's the derivative of 3x? Or what's the derivative of 12x, right? ln of a is just a constant. It's just a number by itself. So derivative of 3x is just 3. Derivative of 12 times x is just 12. So what's the derivative of ln of a times x is just ln of a. Oh, you know what? Hold on. This can cancel, is that right? So if that cancels, this whole piece right in front just becomes a to the x. So on the next slide, because I'm running out of room, I got the end. Here it is. So d over dx of a to the x equals, since e and ln canceled, it just becomes a to the x times ln of a. How interesting. So that's the generic rule for any and every exponential function. So my question is, what happened with e to the x? How come e to the x is a derivative of itself? So if I did this, we already covered this one here. Let's say e to the x, that's a derivative of itself. So what happens here, it becomes e to the x times ln of e. But what happens, technically to the 1, what happens between ln and e? They cancel themselves out. That's why. Those two cancel, leaves us with e to the x. Therefore, yes, there it is. E to the x is a derivative of itself. That's cool. And technically, if you want to, you can say multiply by 1, but then eventually get e to the x. Okay, so let's practice with this stuff. So first exercise problem, find the derivative. Find the derivative of this guy. That should be easy, give you a little bit of space and room here and time. Go for it. That was the easy one. We'll move on to a little more difficult one, but not a bunch. All right, hopefully you guys did it already. So the derivative is it itself, which is 2 to the x, and then it's the ln of 2. So a question comes up is, do I have to move it in front as a multiplier? No, leave it just like that, that's just fine. B, f of x is equal to, and let's get a little bit more complicated. There it is. X to the third power plus 4 multiplying 2 to the x. Now you could distribute, and if you distribute, it gets things more complicated. I wouldn't. I would just use the product rule. I got two things multiplying themselves. X to the third power plus 4 and 2 to the x. So let's go for it. Let's take a derivative here. So the derivative of f of x, now this is a product rule, right? So we probably should write down the product rule here. So product rule says if I take the derivative of f times g, what I do is I take f derivative of g plus g derivative of f. That's the way the book does it. I know we did it a little slightly different. Again, there's like 4 different variations of this. Doesn't matter which one you keep as long as you keep consistent. So let's go for it. I'm going to write down the first function exactly as is. I'm going to take the derivative of my second function, which is 2 to the x, which we just did it above here. 2 to the x, ln 2. Plus sign comes down. Zoom. That's going to be the second function, and then we get to take the derivative of our first function. So derivative of x to the third plus 4 makes 3x squared. And all right, can we do a little bit of simplification? I guess we can. Yeah, I see a 2 to the x in both of those values. Could you keep it out like this as well? Yeah, that's fine too. Yeah. Sometimes the books will simplify it, sometimes they won't. It just kind of depends. But here it is if we wanted to. The derivative formula would be, and let me just rewrite what we had over here before. Let me just quickly rewrite it. You guys don't have to rewrite it because I'm just rewriting what was on the previous slide. There it is. All right, all I'm going to do is I'm going to factor out a 2 to the x. There it is, because that's together in both of them. I can distribute, I guess, or multiply it. So there's ln of 2 times 3 cubed plus 4. I pulled a 2x out of that one, so I got myself a 3x squared, and that's it, and that will be just fine. Okay, there it is. That was the finishing part of 3.4. We had to get the generic derivative for exponential functions, or the derivative for the generic exponential functions. Okay, so let's jam now. Let's jam now to, so 3.4 was the chain rule, just finished. 3.5 was implicit differentiation. Hopefully we learned that one. And hopefully you guys got done homework on that one. 3.6 is now derivatives of logarithmic equations. So so you guys don't get too confused here. What we just did just now, we just did a derivative of an exponential equation. What we want to start now is 3.6. There's no arrow here, so this is the title here, 3.6. Derivatives of logarithmic functions. That's what we want to do here. So technically, is we want to do this. And I'll give it to you and we'll prove it. And then we'll start using it here. Let's do that. It's kind of fun to prove things. So let me give you the rule for it first. The derivative of log base A of x is, dun, 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 is 1 over x ln A. That's the rule. So if you say, hey, Mr. G, what's the derivative of log base A of x? I'm going to say 1 over x ln A. But let's do the proof for it. Dun, dun, dun. Proof for it is y is equal to, so let's say we had a, oh, that's so funny. Okay, that is not a mean face. That is an equal sign that did not make it all the way across. So it should be like this. There it is, even though it's a funny little mean face though. There it is, y is equal to ln of a to the x. Okay, so the question is, what is the derivative of this? Well, the problem is we can't take a derivative directly here. But I could do this. I'm going to add, I'm going to put in a base of a. It is a to the y, a to the ln of the log base a of x. I can put in bases. That's the what we used to do 2 years ago. We used to do algebra 2 and solve for logs here. So I'm going to put a base of a in, and I know it's going to happen. What happens to that a and that log of a? They are gone. So I got a to the y is equal to x. Perfect. Okay, let me, because I'm running out of room here, let me put this on the next slide real quickly here. So, oh, that's what I forgot. Hold on, let me put it in. It's going to be a little bit off here, but in the sense I'm going to put a to the y over x. That's what I want to put in. Okay, so here's what I'm going to do. I'm going to go backwards real quick here. I have this, a to the y over x. I write it over here. Now I'm going to take the derivative of both sides. So I'm going to take derivative with respect to x of a to the y. I'm going to take the derivative with respect to x of x. That's cool. Okay. So what is the derivative of x with respect to a to the y? Oh, we just covered that. It's a to the y. It's its own function, and it's ln of a. Don't forget dy dx, right? Because we took the derivative with respect to y instead of x. Okay, what's the derivative of x? Just a 1. Okay. So now the question is, what do we do in order to solve for dy dx? Divide by all this. So dy dx is equal to 1 on top, and all this on the bottom of the other side of the equal sign. So a to the x ln of a. And the question is, I have to have everything in terms of x instead of y. So what can I replace a to the y with? Yep, and it's on the wall staring at you in red. So a to the y is equal to x. Perfect. Okay, I can erase this now. Let's see if I can do this. Oh yeah. Let me just put down a to the y is equal to x. Perfect. And we're going to replace it, and there it is. It's a 1 over x ln a. That is the derivative of our log function. Sweet. Let's start using it. So, x1, exercise 1, find the derivative. All right, if you can stay ahead of me, perfect, go for it. That would be awesome. I got a is equal to y is equal to ln x cubed plus 1. Let's take the derivative of this guy. All right, so y prime is going to be, so let's see, ln. This is just a log function, is that right? That's just log base e. So our rule says log base a. Doesn't matter, right? So if we want to rewrite this, so we could rewrite this as this right here, log base e of x to the third plus 1, right? That would be just exactly the same. So it'd be 1 over whatever x is. In this case, it's x cubed plus 1. And that'll be ln of, what's my base? E. Oh, wow. Hold on. That's just going to go away, I believe. But let's see. Then chain rule says we've got to take the derivative. What's the derivative of x cubed plus 1? 3x squared. Perfect. And I think I'm almost ready. This is going to be that cancels out. All this stuff is on top because technically it's 3x squared over 1. So how about this? The answer is 3x squared on top, x cubed plus 1 on the bottom. That is the derivative of ln of x cubed plus 1. So I can take, so really if I use ln, whoa, hold on, look at this. If I use ln, the ln and e are going to cancel. Notice what's happening here. It's the function on the bottom and its derivative is on top. Wow. So if we want to make another rule, let's make a specific rule for ln. So I'm going to go here, use a pin. Here it is. So the derivative of ln of x will just be 1 over x. So that was it if it was by itself, right? But then we also know that we're going to have a little derivative afterwards, or a derivative of our chain. There we go. Okay, let's try another one here. B. I need to know the derivative of ln of sine of x. Interesting. All right, so let's put it here. So let's see, I think I'm going to go with 1 over whatever my value is, which is sine of x. And if I want to, I can put ln of e over here. Again, those are going to cancel for me because my base is e. And then we're going to take the derivative of sine of x, which is cosine of x. Oh, interesting. Okay, remember ln of e is going to cancel. So on top, what I have is I have cosine of x on top. I have sine of x on the bottom. And voila, the answer is, anybody remember all the way to trigonometry, what is cosine over sine? Cotangent it is. Cotangent it is. Okay, that's for ln. Let's do one that's not ln. Let's go with f of x equals, well, this would be just log. The log of 2 plus, of course, use some trig functions in here. All right, all yours to go ahead of me if you like, and if you can, go for it. So the only question I have is, what is the base here? If I have a log by itself and there's no indication of what base is here, the default base for log is 10. Absolutely. Let's go with it here. So the derivative of f of x is 1 over whatever the value is. The value is 2 plus sine of x. Then it's going to be ln of the base itself. What's the base? It's 10. Multiplied by the derivative of the value. So 2 plus sine of x, the derivative is cosine of x. Final answer, here it is. I'm just going to put the cosine on top, pretty much. That's it. Everything else remains exactly the same. No problem, no change, no nothing. There it is. Kind of strange at first, doesn't it? Okay. So that's C. Let's go a little bit. Let's get a little more complicated here. Let's go complicated here. Y is equal to ln And let's get ourselves a fraction inside here. Oh, wow. Oh, wow. Okay, let's follow this process. Let's see if we can do this. Okay, I'm going to go dy dx. I could put y prime if I like, right? Y prime or dy dx, both of them will work. Okay, see if I get this. It's going to be 1 over that guy there, which is my value. Is that right? I have ln of e, and then this you can cancel off right away if you like. That's fine too. But then I have, oh man, so again, go through this if you like to. This is a quotient rule on my hands here. That's a quotient rule. Again, write it down. By the time you write it down the 20th time, you have it all memorized here. So f over g prime is equal to g f prime minus f g prime over g squared. Okay, let's see if we can do this. It's not that bad. So let's see. Well, the bottom function is g, the top function is f. So we leave the bottom function totally alone. We take the derivative of the top function. Derivative of x plus 1 is just 1. Okay, not bad, not bad. Minus. We graph, oh, so we have the top function now, f. Okay, here's where the fun begins. Square root of x minus 2. 1/2, right? Because the square root as an x1 is really just 1/2. It's 1/2 x minus 2 to the negative 1/2 this time over the derivative itself is just 1. So really nothing else beyond there, okay? Over the bottom, and now it is squared. Whew. Okay. If you're keeping up, you're doing great. So remember, L and E cancel. So really this one, hey, it's just 1 over this. It's one. It's a reciprocal of this. Oh, that's cool. So let's flip this around. That goes on top, that goes on the bottom. Perfect. Okay, so that's the simplification here. The other simplification is not as fun. Let's see if we can put it together. So this times 1 is just itself. That's the problem. This whole thing right here, this is going to be, let's see, x plus 1 on top, 2 on the bottom because of the 1/2, and then it's x minus 2 to the negative 1/2, so it goes down to the bottom, and it's a square root. Oh, that's cool. On the very, very bottom, that square root now is being squared, so we get ourselves x minus 2. Okay, and then actually gets even easier. That's kind of cool. So this has to multiply the front. So really, this multiplies this. So what is the square root of x minus 2 times the square root of x minus 2? So I'm running out of space, so I got to take it to the next one. And then I got to do this one here. So hold on, wait a minute. Square root of x minus 2 on top, and there's a square root of x minus 2. Those two are going to cancel. Those two are gone. That's so cool. Hold on, let's see if this makes sense. As these two multiply, it just becomes x minus 2. As these two multiply, the square root of x minus 2 cancel themselves out completely. Okay. So rewrite that if you can. Let me rewrite the next slide. So on the bottom, I have the x plus 1. I have the x minus 2. In the front, square root of x minus 2 and the square root of x minus 2 became x minus 2. And then I multiply the second part. The square root of x minus 2 is canceled. So I'm just left with the x plus 1 on top and the 2 on the bottom. All right, if that's the case, I got to do a little bit of work here. So on top, right here on top, let's just do a little bit of work. Let's get common denominators. So we need a 2 denominator for the first parenthesis. And I think we're all good there. So 2 times x, 2 times minus 2 makes 2x minus 4. And then I can just multiply the negative in. So how about if I do this? So this now becomes, so x, 2x minus x makes x, and negative 4 minus 1 makes 5, all over this. And what can we do? Keep, change, flip, is that right? Keep the first one the same. Change it to multiplication, and this just becomes that right there. Ooh, that's a lot of work, guys. So we are done. Final answer is x minus 5 on top. It's 2 times the product of those two pieces there. That was long. Oh, wait a minute. Do you guys remember from Algebra 2? Oh, wow. Look at this. It even says, wait a minute. Do you remember from Algebra 2, if you have a log, any kind of base, but if you have two things that are multiplying themselves inside the log, do you remember how we were able to separate them out by putting a plus sign? There it is. So product inside the log becomes addition outside the log. So hold on. Division inside the log becomes subtraction. So log base n minus log base n. Perfecto. Okay. So I think I have maybe possibly an easier way to do the last problem. Let's do like this. Last problem, same exact one. I see a little quotient rule right here. So if I do this, y is equal to ln of x plus 1 minus sine, is that right? Minus ln of the square root of x minus 2. Oh, you know what? I can simplify that even some more. Hold on, look at this. Let's see. So dy dx. So this one would be 1 over x plus 1. And because it's an ln, remember ln and e are going to cancel themselves. And really the derivative of x plus 1 is just 1. So it just gets me down. Minus, and this guy, remember this guy really is just 1 over the square root of x minus 2 ln of e. And then we've got to take the derivative of the square root of x minus 1, don't forget. So x minus 2 is really that to the second power. So derivative would be 1 over 2 times itself. And then it's subtraction of that times its derivative, which is just 1. So hold on. Oh, maybe it doesn't take that much. It helped us a little bit here, not to get too complicated. I got 1 over x plus 1 minus, let's see what we got here. I got that 1 on top. I got the 2 on the bottom. And this is a square root, right? It's going to go towards the bottom. That's a square root. So really it produces this right here. It produces a square root of x minus 2, which is already there, times another square root of x minus 2. So technically you get another x minus 2 to the 1 power. Okay, let's do some free algebra or arithmetic. Let's get common denominators. I think this guy needs a 2 times x minus 2, and this guy needs an x plus 1. So that's the original one. We need to multiply this by 2 to the x minus 2 and 2 to the x minus 2 on top and bottom. Plus, or minus, sorry. Then this was the original problem, and that gets multiplied by a x plus 1, another x plus 1. All right, let you guys finish that off. Go for it. Just give you a little bit of time. All right, on the bottom of this one here, I got myself that whole piece there. And on top, I have myself 2x minus 4. minus sign over here. Now this has common denominators, that's perfecto. And I got myself an x plus 1. And if I put that together, common denominator is there. So 2x minus x gives me an x. Negative 4 minus 1 gives me a minus 5. Is that what we got the first time around, the D? I'm checking back as well. Yes, that's the same exact answer. So yes, with login functions, you can use the product to addition rule or the quotient to subtraction rule. That is the logarithmic derivative. All right. Okay. I got to show you one more thing as well. So let me in slideshow here real quick. I'm going to jump to this one. Not only is logarithmic like a rule, or not so much a rule, is a rule for, yeah, I could say it's a differential rule, but it's also a process. So just like we have the product rule, remember I have to multiply the first times the derivative of the second plus the first times the derivative of the second. We have a quotient rule. It's a process, right? The chain rule is a process. Well, logarithmic differentiation is also a process. And so let's see what this is. And it's really in order to take derivatives of very complicated functions here. So let's go with it here. I think once we see a couple, we'll be a little bit okay. So exercise 2 says find the derivative. So here's what I'm going to do. I'm going to find the derivative of y is equal to and I'll just let you think about that. Look how crazy this looks. This is a quotient rule that's sitting on top with a product rule. There it is. So I got a quotient rule and product rule combined together in one. Not even thinking about the fact that I have chain rule here. I have chain rule here. This gets crazy. And so if it wasn't for this way of differentiating using logs, we'd be stuck here for hours trying to do a single problem. Okay, maybe not hours, but at least a good half an hour to do the problem. So let's go for it. So what is this logarithmic differentiation way? Let's go with it. So here's what I'm going to do. Just like we did in the last problem, I'm going to plug in ln on both sides. I can do that. That's from Algebra 2. I can plug in the ln from both sides as long as I do the same exact thing to both sides of the equation. There it is. Oh, and just like we did on the previous problem, I'm going to separate this out into its own little individual pieces before I take the derivative. So let's go with it. So I stuck ln on both sides. That's great. I'm going to do the division inside the log, means subtraction outside the log. So this now changes it to ln of y. This will be ln of 3x to the 3/4 multiplied by the square root of x plus 1 minus ln of all that good stuff right there. Right? So I just use the subtraction rule. Okay, and then right here, there's a product. There's two things that are multiplying together. That's cool. Let me undo this one as well. So let's see on the next slide, ln of y is equal to ln of x to the 3/4 plus, right? Because if you multiply something in the log, you can add it outside the log. Perfecto there. Minus, the minus is still the same on the other side. Perfect. Okay. Next piece before I even take the derivative. What happens if I can do this? Oh, remember that little rule that said if it's an exponent on my value, I can take the exponent and put it in front. That is awesome. There it is. This is technically a 1/2, right? I can put this in front as a 1/2. The ln of x squared plus 1. And this one's a 5. 5 gets to go out in front, so minus 5 ln of that right there. Okay, so I can take the derivatives individually. So remember, if it's ln, I don't need to do that ln and e thing on the bottom anymore, because I know they're just going to cancel themselves out. So 3/4 is a multiplier. The derivative of ln of x. Oh, hold on real quick here. There is one derivative of y, of ln of y will be 1 over y. You know what I am forgetting? I am forgetting these. I'm forgetting dy dx. There it is on that side. Okay. So I got 3/4 on my hands right there, but then I got ln of x. X goes down the bottom because the derivative ln of x is 1 over x. This is a fraction, so I got 2 on the bottom. What's going to happen is this guy becomes, x goes down to the bottom, and I multiply it by the derivative of the inside function. That's called the chain rule. Minus 5. Okay, let's see this here. The 3x plus 2 go down to the bottom. Then I also have to take a derivative of 3x plus 2, which is just 3. Oh yeah, there it is. I put it in now. I can erase this now. Just didn't want to. How do I do that? 1 second. Let me see if I can. There it is. Got it for the taskbar. Okay. Erase. All right, got what I need there. Okay, whoa. Messed up there. So let me go very, very quickly, put it all back. That was good. Okay there. I'm one slide away. Sorry, class, real quick here. I messed it up. Let me go all the way to here. There it is. There it is. I'm right there. Okay, let's simplify this stuff as much as possible. So 1 over y dy dx equal to, this one's pretty simple. I'll leave that. The middle term just needs the 2. Oh, look at this. The 2 and the 2 are going to cancel. That got canceled, leaving us just with x on top and x squared plus 1 on the bottom. This one, that 3 and the 5 are going to make a 15. So how about a 15 on top and a 3x plus 2 on the bottom? That's cool. Okay, we still have to solve for dy dx. So 1 over y, remember I could just multiply both sides by y. So here it is, dy dx is really just y multiplied by all that stuff that we just had before. And the question becomes, how do we get rid of the y? What is y equal to? Oh, the y was equal to the original problem. Here's our original problem. Remember, x to the 3/4 square root of x squared plus 1 over 3x plus 2 to the 5th power. And then we're just going to rewrite everything that we wrote before. So that is the process of differentiation using logarithms as a process. There it is. All right, let's do one more. Let's see how this works out. I know you guys are tired. Brain is jamming with all this stuff. So one more problem. So what about this? There's no way I could have done this any other way but this logarithmic differentiation process. So notice I have an x as my base. I also have an x as my exponent. There's actually 2 x's, and they're in 2 different positions. It's crazy. So let's go for it here. So I'm going to stick ln on both sides. Since this is the exponent, this guy gets to go in front. So ln of y is equal to now the square root of x. Wow, funny. Here we go again. I gotta do the look like what? A mean face upside down now. Okay, so square root of x gets to go outside in front as a multiplier. Oh, cool. I see product rule on my hands here a little bit. Maybe we'll see. But anyways, let's go with it. So I stuck ln on both sides, right? Yeah, I did. I stuck ln on both sides, but because this was an exponent, it got to get free and become a multiplier on the outside. That's cool. That's awesome. Let's take a derivative. So derivative of ln of y is 1 over y dy dx. The derivative of this, oh, that is a product rule. So product rule, here it is, f times g prime would be fg prime plus gf prime. That's the way the book writes it. That's the way we'll follow. So our first function is technically square root of x, or x to the 1/2. That stays. We're going to take the derivative of the second function, which would be 1 over x. Plus, now the second function stays. We take derivative of the first, which is the square root of x. Technically x to the 1/2 power, is that right? So that guy is the same thing as this. So the derivative of x to the 1/2 is 1/2 in front. Take 1 away from it, it becomes a negative 1/2. And let's simplify. Let's see. That's going to be okay there. So 1 over y dy dx. So from the previous slide, I have a square root of x over x plus, I gotta think with me, see what you guys got. I have a ln on top of a 2 radical x on the bottom. All right, the question usually comes up, do I have to get common denominators and put all that stuff together? No, you don't. But we do have to do one thing here. Notice this guy here. This is x to the 1/2, and this is x to the 1. So if I do this, if I subtract x to the 1/2 and x to the 1, that'd be a half minus a 1 makes a negative 1/2. So really what happens here, there's a square root of x in the bottom here. 1 of x and 2 ln of x. There it is, that. And of course, what do we need to multiply both sides of the equation by? Yeah, 1 over x. You know what? We actually can combine it. Let's go over it because it's actually not bad. Notice we have both of them are square roots of x. So really the only thing we need is we need a 2 over here. So 1 over y dy dx. I'm going to multiply both top and bottom by 2. But everything else remains just perfectly the same. There's that. Multiply this guy, this becomes a 2, so 1 over y dy dx equals, now I got myself a 2 on top, 2 radical x on the bottom, plus ln of x and 2 radical x on the bottom. That's cool. And let's simplify this all the way through here. So I have one denominator now. It's just 2 radical x. On top, I have 2 plus ln of x over, there it is. Line 2, almost done. Have we solved for dy dx yet? So we're going to have to multiply. This is from the previous slide real quickly here. I'm just going to rewriting it. Let's multiply both sides by y. And as we multiply both sides by y, we get this right here. And we are going to say, what does y equal? Y equals the original problem itself, which is x to the square root of x. And now it's multiplying this whole piece right here. And we have taken the derivative. Wow, this crazy function called x to the square root of x. 2 different variables, 2 different places. But we were able to take the derivative of this. That's perfect. And that'll be the end of lecture for today. All right, hope you guys have a great weekend, and I'll see you on Monday.